All right. Given that there's a strategy named backward elimination, it also makes sense that there might be a forward-looking strategy as well. That strategy is called forward selection. So we started with a big model and we went backwards until we had a small model. In forward selection, we're going to start with a bunch of small models and then we're going to build our way up to a bigger model. Okay? We could also use p-values, right? We could fit a model with no predictors. And then we would fit a model for each possible predictors. And for each of those predictors, we would see, is there an increase, are any of the p-values significant? Which one is the most significant? We would pick that predictor with the smallest significant p-value. We would permanently keep it in our model. And then we would continue this process. So now that we've got the 1 in our model, we would fit a combination of all pairs of 2 and see if any of those pairs of 2 models had significant p-values, both significant p-values, and so on. Okay? When none of the remaining predictors can be added based on the significance level that we're using, we stop. All right? This one, I don't think it feels as intuitive as backward selection, so let's go ahead and look at an example because I think that might help. So here's my empty model. My model with 0 predictors. I do have to stick a 1 there. That's called the null model. That's kind of our baseline in forward selection. And then you can see that I fit a model for each predictor, except for model season, I use both of them since it's information about everything. Okay, now, last week in the R question, someone asked me, do I have to rename everything every time? And I think this is a good example of when, yes, it would make sense to do that, right? You don't want to have to go back and like name it model 1, model 1, model 1, and have to dig around for, what you were looking for. So you want to keep everything different. Let's go ahead and look at all of these models. And I'm actually going to change something up. Instead of using p-values, I'm going to use forward selection with adjusted r-squared. Now I'm not looking for small p-values here, I'm looking for high adjusted r-squared. So model no, my r-squared is 0. That's very bad. So pretty much any predictor is going to represent an improvement. I see adjusted r-squared for high temperature is 33, so that's the one to beat. Low temperature is 0.019, so that's basically 0. Average temperature is somewhere in between that, so high temperature going forward is the one to beat. I've now seen models for the season, cloud cover, precipitation, and weekday. These are all on slide 39 if you're following along. None of them has an adjusted r-squared higher than high temperature. So high temperature is still the one to beat. And since it had the highest adjusted r-squared, what I'm going to do now is permanently keep high temperature in my model, but I'm going to now repeat the process of adding a variable at a time. Okay, so you see I've got a bunch of new things. High temperature is always in the model, and I've added a second variable. Okay, so for the model with high temperature and average temperature, high temperature and low temperature, I've got 40. I've got 40 here. That is an increase, so we're good with those. One of those might be the one to beat. You can see here I've got season, cloud cover, precipitation, and weekday. And it's very close, but the highest r-squared goes to cloud cover, right? Highest adjusted r-squared, excuse me. It's just edging out precipitation here. So what I'm going to do now is that knowing that the model has high temperature and cloud cover, it gets me the highest adjusted r-squared, I'm going to keep both of them in my model. Okay, that's what this says. So high temperature, cloud cover. I'm going to repeat my process one more time and add the remaining variables one at a time to these two variables. Right, so starting to run off the screen, and I think you all can see at this point that forward selection can be quite tedious to sit down and code, which is another reason that I prefer backward selection, but you're welcome to use either way. I've added everything here, so adding low temperature increases it a little bit, adding average temperature increases it a little bit, season increases it a little bit, nothing really to write home about. Bump the TV there. Cloud cover, that option B in there. That's the one that we have. Model precipitation, though, does add a whole big chunk, right? It goes from 42-ish, 43-ish to 46. So I'm going to keep that one. Weekday gets it up to 44, but not as high as 46. So the model with high temperature, cloud cover, and precipitation has the highest adjusted R-squared. So I'm going to repeat this one last time. I hope that this model is starting to look familiar to you, right? We are starting to get to the same spot that we came to via backward selection. So yeah, it's totally running off the screen here. But you can see I was at 0.466, I think. This is 0.465. That's not helping. 0.465, 0.462. None of those are helping. So, oops, I went backwards. Wrong way. 0.429, 0.475. So I've added weekday, and it did increase a little bit, so I could stick with weekday there. Okay? I could keep repeating this process, right? I could keep going on forever and ever and ever until I've added them all back in. But I'm not seeing big increases anymore, right? They're like really tiny, very marginal increases. So I'm actually just going to stop with the model with high temperature, cloud cover, precipitation, and weekday. I feel pretty good about that model. That's not quite the same model as the one we found with backward elimination. But basically what we do, if you're going to use both and they arrive at different approaches, you just pick the one with the highest R-squared. That's kind of the tiebreaker, is the adjusted R-squared, excuse me. Okay, so we learned now, I showed you examples of 2 different model selections. We actually have 4 different model selection techniques. You can either go forwards or backwards, and you can use either p-values or adjusted R-squared. So you can sort of mix and match, so there's 4 options. Backwards and forward selection tend to arrive at a model that's at least close, and we just use adjusted R-squared as the tiebreaker. But the choice between p-value and adjusted R-squared actually sort of depends on what you're trying to do. Okay, so sometimes the goal of the regression model is just to make really good predictions. And in that case, we want to use adjusted R-squared. So that's actually very common in machine learning or computer science applications. Really, you're just trying to maximize your prediction accuracy, so you're going to end up picking a model based on the adjusted R-squared. If instead you don't care so much about predictions and you care more about understanding the relationships between the variables and sort of looking at which variables are statistically significant, then you're going to use this p-value approach, right? And especially if you want to know what's important at the cost of a little bit of your prediction accuracy. So I think a good example would be maybe to fit like the presence of, we'll say maybe cancers in the population, right? We might want to be able to predict how many cancer cases there are going to be in the population so we can appropriately allocate resources. So if you're building a model to predict the number of cancer cases with the goal of, giving resources to people, you might want to have good predictions and you would use the R-squared approach. If instead you wanted to understand why are there differing numbers of cancer cases and can we get rid of things to decrease the number of cancer cases, that's more of the statistical looking approach, not computer science statistics. That's what we tend to be doing. So you would use p-values instead. And that way you could find variables that were helpful to know to predict increased number and decreased numbers, right? So there's different goals. And they're pretty similar, but what happens is that adjusted R-squared tends to include more predictors in the model. So it can be beneficial in terms of the prediction accuracy to include lots of things, but if you're looking for patterns and relationships, sometimes we want to get rid of them and just look at very streamlined models with smaller numbers of predictors, because those are often easier to interpret what's going on between the different variables.